Hey YouTube, it's Dimitri, and today we're going to discuss multicollinearity in decision trees. So yes, this applies to all decision trees. People are going to be up in arms complaining, right, Dimitri? It's one of the strengths of decision trees. There's no multicollinearity, and it's partially true, it's partially not true. You have to be extremely careful with this. And so before I get going too much, let's just dive on in. Okay, so what is a decision tree? So in simple terms, it's really just some sort of tool that we're going to use, and we're going to take data and we're going to segment it down from the root, and we're going to segment it into branches, and we're going to keep segmenting it over and over and over again until we get to these leaves at the end, and we stop splitting basically when we get to some sort of state here. I'm not going to go into too much of the detail. You can stop early to prevent overfitting, and you're going to end up with basically predictions at the end of this. You can do categorical and you can do regression. For this example, for simplicity's sakes, we're going to talk about categorical. So to predict categorical variable here, so some sort of target, let's say it's binary, in this example with 0 and 1, there's going to be some sort of algorithm here that's going to split the tree, and it's going to try to get uniqueness within the groups here. So in this example here, right, if it's blue, it's going to be 1. If it's red, it's going to be 0. And we're going to try to get some sort of split. So in this bottom left-hand corner, you can see this is a perfect split. We're going to use the algorithm called the Gini index here. And this is going to be used to basically calculate out what is the purity within the split. So in this bottom left-hand example here, let's say, I don't know, we pick some variable like age. And if you used age to predict something that's based on 0 and 1 here, let's say, I don't know, let's say your height versus your age or something. If it was a perfect split, what would happen is if you said, okay, you're less than, I don't know, 18 or you're greater than 18, and you could split this into categories, a perfect split will get you a Gini coefficient of 0. Now, realistically, this hardly ever happens, and if it does, you're probably overfitting your model. But again, just for simplicity here, a lower Gini is better, so it has lower impurities. In the bottom left-hand pane, right, for example, if we had like a red dot on the left-hand side, it would no longer be a perfect split. The Gini index would be very, very small, close to 0. And if you had a perfectly random mix here, you would have a Gini coefficient of 0.5. So, right, in this case, we're doing categories. We're predicting basically two things. The maximum difference here could just be a randomness of 0.5. Now, keep in mind, you can have a better coefficient, Gini coefficient than 0.5 just by pure random luck. So keep that in mind. So what is the issue here, right? The claim that is being made is that decision trees are not affected by multicollinearity. So this is what a lot of people are claiming out there. If you Google multicollinearity and decision trees, it will come up and it'll say they are not impacted by multicollinearity. This is partially true. However, it can create dangerous models simply because people just ignore it now. As soon as I tell you, okay, multicollinearity does not impact decision trees, people throw the idea out the window. They think, I don't need to learn this. It makes no sense. I'm a data scientist. So let me explain a little bit more in detail why this is important and why it will actually bite you and build basically poor models, and they will fail because you have multicollinearity in your decision trees. So first off, let's define what is multicollinearity here. So it's high correlation between two or more independent variables in a regression. So if you have a regression equation, it's, y equals say alpha plus beta 1 x1 plus beta 2 x2. The x1 and the x2 are two independent variables. If they are highly correlated, it's going to be multicollinear here. So there's no sort of threshold either, right? We say highly correlated because there could be some issues. But the reason why multicollinearity is such a problem is, one, it's going to be a weaker statistical power, making the p-values unreliable. 2, the coefficients or the slopes lose meaning, and 3, high variance estimates, which are unstable. So what that really means here is that you have two variables that are almost the exact same predictive power on what we're trying to predict here. And I'll show you an example here in a second when we get towards the end of this presentation. But really it's like saying, I don't know, would be, let's say you did US dollars and you did, I don't know, Canadian dollars or something. They might be different values, but the exact predictability of them, like there's some sort of, conversion rate to get from dollars to Canadian dollars and back. They would have basically like a solid mathematical relationship. And so it'd be really, really hard to figure out whatever they're trying to predict against because the relationships are the exact same. So it's really just confusing, but it makes your coefficients, the p-values, when you look at them in a regression model, unreliable. And sometimes you have a really good model, you add a few data points and boom, the whole thing blows up. So it's important because it makes linear regression models basically not stable. So again, decision trees are not regression models. You can do regression with decision trees, but they are not linear regression models. I know. Bear with me here, guys. Give me a second. More specifically, let's break down what multicollinearity really is. It's really just referring to a linear relationship or some sort of correlation here within a regression model, okay? If you view this concept more theoretically from a broader perspective, we're just really concerned with correlation. So multicollinearity is just a fancy term to say, okay, when we have high correlations and we're actually working on regression models, let's come up with some term here to label this. And to do that, we just call it multicollinearity. And then I don't have to sit and explain this one for 20 minutes on, these variables are, highly correlated and it's a problem and it's in a linear regression and explaining the whole framework and then explaining why the beta coefficients aren't reliable and also why the p-values that have those beta coefficients aren't reliable in themselves. And it creates a whole issue, which is why we use the term multicollinearity. But again, we're just going to use the general concept of correlation between two input variables into some sort of model here. Technically, nonlinear models have similar issues here. So correlation-wise, you can have nonlinear correlations. That's for another class, though. But there are other sorts of correlations, such as Spearman's and Tao's. There's different sorts of correlations, which we're not going to talk about in this video. But you can have, for example, non-linear high correlation. So it's a possibility. It's not just a linear thing. Okay, so now why is multicollinearity not a problem in decision trees, and why is it specifically listed online and in papers that it is not an issue here? So this is due to one of the strengths of how a decision tree actually functions and works. So the way that the tree is split is basically you have your data and you're going to come to some variable you're going to add in and see if it's a good split or not. And you're going to say variable A, let's say, and variable B, we're going to see which one's a better split. And you're going to split it and see the purity or the impurity, depending on how you want to look at this. You're going to see basically how pure it is, and then you're going to do the other variable and see how pure that one is, and whichever one has a better prediction here, so you have more purity when this splits, you're going to select that variable. So if you had two variables that were extremely highly correlated, so variable A and variable B, and variable E was just more accurate by one observation out of a million observations, for example, it will be selected because it has a higher correlation with the dependent variable. So the variable, the target variable, the one we're trying to predict here. And since it has a higher correlation, it will be chosen. And on that branch inside the tree, that other variable will be thrown out and will not be used because that relationship will already be picked up inside the decision tree here. But the big problem with this though, okay, is that you can have spurious correlation and logic here. So what do I mean by this? Spurious correlation here applies to just general regression here, general modeling. So spurious regression is typically used within time series. Spurious correlation is going to be something, just a general concept and idea. And it's when two variables are correlated, but no meaningful relationship exists here. So the big one they always give in school is, when ice cream sales go up, murder rates go up. When ice cream sales go down, murder rates go down. And of course, there's a factor being the weather in the summertime, which ties these all together. And you can even Google this, guys. If you want to go online and Google, you can find really crazy correlations of things that make absolutely no sense. And they're so absurd that we all agree they're ridiculous. But in practice, there are often relationships we think are related because there's high correlation, but they're not really causation between the two. And so the problem with this from a data science decision tree perspective here is often we see people taking massive data sets. So even like in banking, for example, we could have 1,200, 2,000 variables, something crazy. And we need to narrow that down. Decision trees are a way to do this. We can build a decision tree to model the problem we're modeling, or even to do variable reduction as a different methodology here. But you throw basically everything in the kitchen sink here. So what we're talking about is we put all the variables in, and then we can just run the tree, and we can let the computer do all the algorithms, do all the splits. We can, trim the tree back, do a few things to prevent overfitting, and come up with some sort of model at the end here. But the problem with this is that if two of the variables that end up going through this process that I mentioned are extremely correlated, the issue is what if we have one variable that is complete nonsense and one variable that is extremely meaningful? But the one that is complete nonsense has one or two observations or some slight edge of correlation over the meaningful variable here, okay? what's going to end up happening is you're going to end up selecting the wrong variables in the model. And again, guys, if you had 5, 10 variables, I get it. But when you have thousands of variables, this is where you start running into issues that you have to narrow these down in a sort of fashion here, which is why I would recommend like some sort of clustering algorithm to get variables that are highly multicollinear together, create different clusters, and then actually go through the regression here itself, or the decision tree, or the neural network, or whatever you're working on. And you can narrow down and look at the top variables from each of these clusters that are highly collinear, or multicollinear in our case that we're talking about here. So let's do a quick example. Let me just show you kind of what this would look like in a real world play example here. So credit risk and quantitative finance is a very, very popular area to use models. Gradient boosting trees, so GBTs or GBM trees, are really common. So they work quite well for this. What we're modeling though, is we're going to be modeling the probability of default on a loan. And what our loan's going to look like here is we're going to have observation numbers. These will be like customer IDs or something like that. And then we're going to have our target variable, which is going to be default. If basically you have a 0, the loan has been paid in full, or the loan basically didn't default, maybe it's still in the process of paying, but no payments have been missed, there's no default. And then if the value is 1, it's going to be that customer defaulted on the loan, did not pay it in full, and we want to model this. So this is called PD, probability of default. It's done in credit scorecards, goes into the equation for expected loss, which is required for regulatory purposes, as well as kind of scoring out customers. Now, you're going to have a bunch of input variables here, and the variables commonly used for these sorts of models are like LTV, which is loan to value ratio, oldest trade, utilization, and then we're going to throw in a ridiculous thing called shoe size. So the customer shoe size, again, this is not used in practice, but for illustrative purposes with our example here. I'll briefly explain these though. So as I mentioned here in practice, you'll typically have probably hundreds, if not thousands of variables, depending on your data sources and quality of data and all that. But common variables like LTV, for example, so loan to value, a really low value for loan to value. So if you have a really, really small loan and the asset that you're loaning on, like your car or your house, for example, is really large, it's low risk. So imagine you put down, I don't know, the loan, I needed to borrow $10,000 and it's a, I don't know, $300,000 house here. So a really, really low loan to value is low risk. A really high one, so let's say I have, I don't know, a $300,000 house and I borrow $350,000 because I need that extra 50 grand to renovate the house and whatnot. The LTV is over 1. It's extremely risky in this situation. So it's a good predictor though of credit risk. Oldest trade is how many days or months, for example, that you've had an account on some sort of bureau here. So typically people that have had credit, so loans, credit cards, experience in finance, right? The longer that is, the more experience you're going to have, the less likely you are to default, for example. That's a good variable to use. Utilization here is how much of all your loans here. Typically it's viewed as all your credit lines, for example. So let's say you have, I don't know, 5 credit cards and a mortgage and an auto loan and all that. What they're trying to figure out on these, and more specifically, it's typically just used in credit cards. But if you used it in the credit card example here, what it would be is say, okay, I used, I don't know, $1,000 and my limit was 5,000. So 1 over 5.2, my utilization rate's 20%. If your utilization rate is like, this first example, 0.981, that means you're using up like the maximum amount of credit. You're probably pretty financially stressed and you're not in a good situation here. And then shoe size, we just made up random data points here. For shoe size, we'll put in some values, 7 to 14, it looks like in this example. But of course, in the real world, you would have millions of observations in finance. So millions, I've seen even terabytes of data, just because there's so much data to deal with in a lot of these examples. And that's why it's important here to use something like a decision tree or cluster analysis to kind of narrow these down. And let's say we just built this simple tree here, LTV being the first split. And then of course we split to the left, we have oldest trade, and we end up with 2 predictions here, which are the green circles. And then we split to the right, and let's say utilization and shoe size are highly correlated. So if you look at this bottom right-hand table here, you'll see that the shoe size, or the shoe itself, with default is 0.75% correlation, and the utilization rate against the default is 0.73. So in this case, shoe size is going to be slightly more correlated with the dependent variable we're trying to model. So when it does a split, you get more purity by using shoe size over utilization, and we would end up wrongly selecting or incorrectly selecting here shoe size, which makes no sense. Now, also note here too, so I'm talking about the correlation again between each variable and the dependent. That's how the splitting is done. But the multicollinearity issue here, or the correlation between the two variables themselves, if you look at utility and shoe, it's 0.981. So that means that they're extremely correlated. Now, again, this isn't true in the real world. I'm just making this up. But you'll notice here that utilization gets pushed out because they're so highly correlated and because shoe size slightly outperforms utilization rates and ends up selecting the wrong variable. And then again, underneath that, the tree continues to split and you have oldest trade. I have it twice in here because I'm assuming, let's say it's, I don't know, there's different ranges of them. So like the left box might be, oldest trades less than 100 days or 100 months or whatever. And then the right one might be, I don't know, oldest trades less than 100 days or more than 350 days with other like stipulations on it. So you can have them in different branches here. And then again, we have the leaves here at the bottom for the prediction. So this is just a simple example of why you would need this. Now imagine this massive tree with tons of variables in here. You're going to have to go back and actually look at these and figure out why they're in the tree and if they make sense. And in the practical real world, it gets extremely challenging because often things in the economy, so in finance, for example, economic variables and financial variables often all seem related because they're all kind of intertwined, but often one's not actually causing the other one. There could be like a variable in the middle. There could be 15 different lags or delays between them, or it could just be spurious regression and it's really correlated today. And then in 6 months from now or a year from now, that correlation falls apart and your model doesn't predict very well. And of course, to wrap this whole video up, why do we even care? Dimitri, just let me throw everything in the model and it'll just pick whatever I feel like. And if we have this issue, who really cares? I'll just automate and rebuild a new model and a new model and a new model. Well, this comes down to some of the issues here with data science and machine learning specifically here. There's a proactive approach and a reactive approach here. So think about this from a quant finance perspective in managing risk. Proactive meaning forecasting. So the model needs to hold up with all future data, and I want to use it to forecast out further. Again, model development is extremely expensive. So even if you try to automate these things, it's expensive to hire people to maintain these. Also, from a finance perspective, often when we book things, we have to hold those assets on book for a long extended period of time. If you make a mistake and it's not working very well and you don't predict out in the future very well, you could take massive losses, right? Even if the model quickly catches up and corrects the mistakes, all those loans and all those assets, for example, that are purchased, often you can't get off the books. So think about making like a 30-year mortgage. You're stuck with it for 30 years. If it turns out to be a dud and you get like a year in or even like 2 months in and you realize it sucks, you're going to have to figure out someone else to buy that. You have to offload it to someone. Most people are going to realize it's not good and aren't going to buy it. So that's being very proactive. That is forecasting into the future. Again, you could be reactive, which is what many technologies do. This is this automated process people think about like, oh, we can automate machine learning and data science, which you can do with statistical models as well. It's just not responsible. But this is really just looking at historic data. It's being very reactive. So we wait for something to happen, like we wait for the data to come in, and then we go, oh crap, our model's not working. Let's refit and restructure and build a new tree. And then we'll use that tree. And that tree works for a few loans, and all of a sudden, oh crap, it's not working again. You have to build a new tree. You're always looking backwards. It's like driving a car, but looking through a rearview mirror. It doesn't matter how much you look through the rearview mirror, you're not going to be able to drive forward. And this is one of the massive criticisms we see with machine learning, is that it is very brittle. And when you apply this to quantitative finance methods, things that are time series based, time series are not easy to work with. Even credit problems, for example, will somewhat deteriorate and break down, and they become very brittle in the sense that they just break quickly. So every time we build these models, they don't work well. Now, again, you can make decision trees very good and more robust by avoiding this multicollinearity issue, because this is one of the key drivers on why they're kind of breaking down, at least from what I have seen in the industry and practice here, with people kind of playing with financial data and refitting them across time. Number two, though, is explainability. So everybody's talking about explainability. It's kind of talked about in a weird light. I'm not a fan of the term in itself. It tries to make it seem like it's post hoc or like we've already done the analysis. We're being very reactive here. But in general, there's regulations, there's equality and fairness. So on these sorts of things, right, you want a model that's very predictive, forecasting, proactive. We want to be able to make great decisions here. Now, from a regulatory perspective on this, we want models that we understand well. If you have nonsensical variables just being thrown in because of high correlations, regulators aren't going to be happy because it makes no sense. From an equality and fairness perspective on customers, so again, going back to our finance example with credit risk here, you can apply it to other areas as well. let's say we're making loans and we're doing it off your shoe size. This is complete nonsense. This is a discriminatory practice I've never seen before, but it's definitely something that's discriminatory. It's not equal. It's not fair. It's against the law. Again, if you have these sorts of variables coming in, that's an issue. Even if you have variables that are legal that you could use, again, sometimes you're going to have weird transformations of them, or perhaps the way it's structured in the tree, or since it's not really predictive, you're basically judging it off of something that makes no sense. So equality and fairness is a big deal here. You shouldn't just throw stuff in to throw stuff in. It's not good for your customers. And then finally here, decisions, policy, and action here. If you have some sort of model and you want a decision off it, right, we need to make sure we're making the right decisions based on equality and fairness, but also on profitability, for example. You also have policy and action here. So let's say, I don't know, we want to decide we're going to go into a new product line, or we're going to target a new customer base. We want to make some sort of policy here. We're going to take some sort of action. Often we can use these models and say, okay, if we adjust, for example, LTV in this loan, we see LTV for some reason splits at, like, so let's say 50%. If your LTV is greater than 50%, it's way too risky. If it's less than 50%, it's extremely safe. You might be able to action that somehow, or create some sort of policy and say, okay, if we have LTVs that are greater than 50%, we don't want to consider taking on these risks. We don't want these sort of customers here. And you can use the model itself to help kind of give you some insight to make some policies or make some action here inside the firm, such that you can use it for, generating your business or generating some sort of strategy. It gives you insight. But if you have some sort of nonsensical variable like shoe size, you're going to have crazy people. And trust me, I've been in business and banking and finance and academia for so long, all these years of my life. You will see people doing crazy things like, oh, shoe size is so meaningful. And they'll come up with some logical reasoning on why shoe size makes sense and how you need to create some sort of plan and action. You're going to go out and, I don't know. So you're going to develop a credit card line for those with different shoe sizes. So, this is like for the big shoed people and small shoed people. And I don't know. You can do all kinds of crazy stuff. Don't fall down the rabbit hole on these. Again, creating decisions, policy and action planning, and strategic planning here is going to be horrible if you don't fully have real relationships inside the model. And then finally, model monitoring here, which seems to be somewhat unique to finance. Again, I would highly recommend and encourage everybody in data science and tech and marketing analytics and all these areas, really focus on model monitoring. So once you implement a model, you've built it, say it's a decision tree here, right? We want to know where the weaknesses are. We want to know why the model is going to fail. So let's say you put, variables into this model. Maybe we have too many layers in the tree and we're kind of concerned the tree's a little bit overfitted, but we think they make sense here, right? We know in the back of our minds, if it starts failing, it's probably because we have too many variables and it's overfitted, right? So that's a problem that we've identified from the model development process here. You can create model monitoring here. For example, monitoring all the variables in the last branches here or specific level in the tree. And you can use that to kind of predict when it's going to fail here. Now, you can't predict if it will fail and it's going to deteriorate if you have no idea what the problem actually is here. So if you've just thrown all these variables in and they're highly correlated and you picked them based off correlations, not causation here, or some sort of business logic, it's going to be extremely challenging. So again, model monitoring is going to make this a lot better and a lot safer to use your models. But if you have nonsensical things going into the models, or you're trying to automate this to the point that there's no human intervention or understanding of the model itself, this is extremely dangerous, and this is why we should care. So anyways, those are my points. That's why multicollinearity should be a consideration in a decision tree. So again, it's not actually in the final tree itself. It's an issue when you go into variable selection and actually designing and growing out your trees here. So anyways, thanks for watching. Don't forget to like, share, and subscribe. And as always, until next time.